Today we're going to look at momentum and impulse. Before we get into the new topics of momentum and impulse, I want to review a little bit of Newton's laws, because momentum and impulse is really just an extension of Newton's three laws. If we remember from earlier in this year, we learned that Newton's first law was his law of inertia, which simply stated that an object at rest would stay at rest and an object in motion would stay in motion without any outside forces acting on it. So momentum is going to deal primarily with the second part of that law, where momentum is defined as inertia or mass in motion. So this is where we kind of focus in on the second half of Newton's first law of that object in motion. Momentum is going to be notated by the letter rho, which really looks like a lowercase p, and so you can kind of use those interchangeably. And as I said, it's defined as mass in motion, which means that simply we need a mass and we need some sort of motion, and we need that to be constant motion, as the definition of inertia deals with constant motion. The units for momentum are built off of this idea of mass, or kilograms, and velocity, meters per second. So the units for momentum are simply going to be kilogram meters per second to represent 1 unit of momentum. So as Newton's first law says, an object in motion will stay in motion unless acted on by an outside force. So momentum is based off of the idea that in the absence of any outside forces, the momentum has to be conserved, which takes us to another law of conservation like we had with energy, but here we have a law of conservation of momentum. Simply stating again that without any forces, the velocity that an object has to begin with will maintain throughout the rest of its path. In the event that there was a loss of velocity, then an object would lose momentum. Now, going back to this law of conservation, we can transfer momentum from one object to another, but the total amount of momentum that we have must stay the same. So if an object were to lose 10 units of its momentum, then some other object would have to gain it. And the only way that we'd be able to have that transfer, to have a change in momentum, is through some form of collision or some form of force. When we have that force that causes the momentum to change, this causes what we call an impulse. And that impulse is going to still tie into Newton's now second and third laws, where we described that collision that would occur, or that force occurring, and how it would change the object's velocity or cause an acceleration. So impulse occurs when we have a change in momentum, and it can only occur in the presence of a force. So I'd like to take a minute and hop back to Newton's second law for a quick refresher, and then tie that into the impulse systems. Now, to close off this idea of impulse, we said that impulse is equal to the change in momentum, which is simply mass times the change in velocity. Since momentum is measured in kilogram meters per second, impulse can also be defined as being measured in kilograms meters per second. But we can also see impulse being measured by the second part of its equation, that idea of force and time. So force is measured in newtons, and time is measured in seconds. So impulse can be defined as kilograms meters per second or Newton seconds. So all of these can be used interchangeably. Now, this idea of impulse is going to ultimately lead us into collisions, because again, I can only have an impulse if I have a force, and that force is going to have to result when one object strikes another object. So the next thing we'll get into is collisions, where we'll talk about elastic and inelastic collisions and how momentum can be conserved there. More on that tomorrow, though. So Newton's second law was simply stated F equals ma, force equals mass times acceleration. And I'd like to remind you that acceleration is simply a change in velocity over some amount of time. So Newton's second law could also be written as m delta v over t. So when we have the force, it causes the object to change velocity based off of its mass. We're going to take this idea of Newton's second law and use this to create that impulse equation. So my momentum will change if I have a force that acts on other objects. So if that force causes an object to change its momentum in some amount of time, then an impulse will have occurred. Typically, we see the impulse equation written something like this, where we would not need all four parts, but any of the two parts would do. So impulse can be defined as a change in momentum. It can also be defined as how the object's velocity changes, because in a collision, typically the mass of something isn't going to change, but its velocity could increase as a result of that collision or decrease as a result of that collision. And then finally, impulse can also be described as how that force over a certain period of time would affect the object's motion. The idea of impulse is what most engineers end up using to create and design safety mechanisms in rides, vehicles, and other daily pieces. The way this ends up working out is if a car is traveling at 60 miles an hour, then the passenger inside would also be traveling at 60 miles an hour. In the event that that car were to collide and crash with a wall, the person inside would go from having an initial velocity of 60 to a final velocity of 0. Whether that person is in a car that has an airbag, whether they're wearing their seatbelt, no matter what, that person has experienced the same change in momentum. But the difference is these safety devices, like seatbelts, like airbags, like crumple zones, help to keep us safe by reducing the force that we feel. So if I'm in a car that has no airbag versus being in that same vehicle going the same speed, but this time I have a seat belt to hold me in and I have an airbag to cushion me when I hit this wall, I'm still going to go from 60 meters per second to 0 meters per second. So my change in velocity is the same for both occurrences. The mass of myself and my truck would be the same for both occurrences, which means that my impulse in both cases would be the same. So having a seatbelt and having an airbag doesn't affect the change in my momentum, but what it will affect is going to come back to this idea of force and time. So if my impulse in both cases is the same, then what is different? When I have a car with an airbag, what happens is the time that it takes for me to go from 60 to 0 is going to increase. So instead of taking 1/10 of a second, maybe it takes me 1/2 of a second. As a result of that, the force that I experience is going to decrease, meaning that I'm less likely to have injury, or at least severe injuries. So with impulse, we're typically looking at the relationship that plays off between force and time. But just because the force and time is different does not mean that that change in velocity or that change in momentum is. So my change in momentum is the same for both cases, where my force and my time are not. You might recall that this kind of starts to sound a little about like Newton's third law, where we talked about those equal and opposite forces, where a bug colliding with a vehicle, we talked about how both the bug and the vehicle would experience equal forces. The difference being that the bug, having a very small mass, would experience a large acceleration, whereas the vehicle with a large mass would experience a very small acceleration in result. Okay? Or the bug would have a huge change in velocity where it would be going in one direction, stop, and then turn around and go in the other direction, whereas the vehicle would have a much smaller change in velocity in that same instance of time because it was moving and it simply now starts moving with slightly less velocity, if at all. So this now extends to that idea of impulse, where the impulse that one object feels is equal to the impulse of the other. But where the force was based off of the mass and the acceleration, my impulse is going to be based off of this idea of the mass and that change in velocity, or the force and the time aspect.